one might ask, how would standing waves look like? Okay, this is a picture. Actually, it's part of a video that we'll look at in 1 second. So we see here at both fixed ends. So you see here at both fixed ends, we have nodes. And we have a node here in the middle. So this one here, this particular image, corresponds to the second harmonic for the oscillation of this string. So this is a node in the middle, and a node at the other fixed end. And between any two nodes, we have an antinode. So that's an antinode here and an antinode here. The distance from a node to a node, or from an antinode to an antinode, is what we call a segment. So this is one segment. This is another segment. The length of a segment, if we measure the length of a segment, the length of a segment is half the wavelength. So for instance, if we measure the length of this string here from here to here, we get the wavelength for this particular wave. We get the wavelength because we have two segments, or two half wavelengths. Okay, let's see it play. Okay, you see here the string move up and down with maximum amplitude. That's the antinode. Here it does not move much. That's the node. Does not move much. That's the node. And we have a standing wave. You don't see the wave moving towards the left or towards the right. That's why we call it a standing wave after all. Okay, now let's look at this other example. In this case, we are going to see more harmonics. We'll start with what's called here the first mode, or the fundamental frequency. And then we'll go to the second harmonic, third harmonic, and fourth harmonic. Okay, I'm going to try to run the video. You see it here. Okay, I'm pausing it. So you had a node here, and an antinode in the middle. That's the fundamental frequency. Remember, the distance between two nodes is half a wavelength. So we have one segment here that's half a wavelength. If we measure the length of this particular device, the length from here to here, that's half a wavelength. Or in other words, the wavelength is twice that length. Okay, going back to it, let me go back and run it. You see then the antinode at the middle. Okay, here we have the second harmonic. So we have a node here, a node at the end. Remember, the ends are fixed, so we are going to have nodes all the time there. And then we have an antinode here and an antinode here, and a node in the middle. So we have two segments, one segment, two segments. The length of each segment is half the wavelength. So in this particular case, we have two half wavelengths. So the length device is actually equal to the wavelength of the wave that we observe here. Now let's continue to run it. Okay. Next, we are going to see the third harmonic. Remember, for the fundamental frequency, we had only one segment. That's all what we had, one segment. So the length of the device in that case was equal to half the wavelength, and we would get the wavelength by just multiplying that length by 2. And then for the second harmonic, the length of the device is equal to the wavelength. Now for the third mode, third harmonic, we are going to have two nodes in the middle and two nodes at the end. So we have three antinodes in the middle, or three segments altogether. One segment, two segments, and three segments. So one node, two nodes, and then the ones at the end. The ends, they are always nodes in this case because they are fixed ends. Okay, we go to the fourth harmonic. Okay, you notice here, again, nodes at the fixed ends, but then I have an additional node in the middle, three nodes now instead of two. And then we have 1, 2, 3, 4 antinodes, 4 segments, 1, 2, 3, and 4. This is half a wavelength, this is half a wavelength. So half of the length is equal to a full wavelength.